Like poke my finger. I can't believe enough how your finger.
I
mean, yeah.
I went to fire yesterday. So who are my engineers? Who are my engineering students in here? I'm so sorry. Can you explain to me what a moment is in engineering? What is a moment of force?
Name one good reason for engineering.
A moment of force is something, it's something that causes an object to rotate. So that's what it depends on the amount of force and the point at which the force is active. Okay. That object is said to be in inertia if all the moments cancel each other out. It ain't rotating anywhere. In a two-dimensional object, if we can represent a two-dimensional object by a region in the plane. The lower curve in the x-axis of rotation goes. Model for a thin lamina. Black. R here is a thin, and we're going to make it homogeneous. Like a little bitty plate. Homogeneous means that the density at any point is the same. Moments with respect to the y-axis, the forces that act on this region and make it want to swing about the y-axis. So if I apply a certain force here and it makes it want to go around the y-axis, that's a moment with respect to the y-axis. We're going to denote that with a big M and a little subscripted y. The moment with respect to the x-axis acts in this way, acts to make this rotate about the x-axis. There's a point in this lamina at which all of the moments cancel each other out, and it's essentially a balance point. It doesn't swing in any direction, not one to tilt about the x-axis, not one to tilt about the y-axis. That single point in this region at which all the moments cancel each other out is called the center of mass. So the moment with respect to the x-axis can look like this, mx. The center of mass is a point in this region at which all moments cancel each other out. Balance point.
So like regardless of like how you're moving it all which way, or that like the center of mass like stays constant. Like don't spin.
Well, we're not moving it, right? An object by itself has a tendency to want to move because there are forces acting on it. So if you're constructing something and if I set it down here on the table and it wants to fall over in one way or the other, that's because there are moments acting on it. And it's a thin sheet, so it doesn't have like the lenses to hold it up like my glasses did, right? It wants to fall over because there are moments acting on it. That balance point is an ordered pair that we're going to denote using symbols that represent average, like average X, average Y, X bar, Y bar is the center of mass. All of these moments depend on where the point is in the region, how far it is from the axis that it wants to move about, and whatever force is acting on it. So if we can print things homogeneous, then we don't have to worry too much about the forces, then it's more just a matter of distance. Now, a point right here is farther from the y-axis than say a point right here. In order to find the center of mass, we kind of look at this, and each of these has some sort of function. If I think of that as some sort of plate, and I want to balance that plate on my finger, then I have to take into consideration the regular shape. Then it looks like maybe the balance point might be, I don't know, somewhere about right here. Maybe here, I don't know. Trying to balance it on my finger. I'm going to go hunting for this balance point by finding the balance point of individual strips of this thing, and then we'll average them all out. Average them all out will have something to do with the shape of the region, or its area, or its mass. What's it? Area mass.
Is it like just areas like how much like space it takes up, whereas mass is how much is like in that space?
It has to do with density. Right? Mass is area times density. Right? Mass is area times density. Like the mass of a region by taking the area of the region times the density. We're going to take the density at each point to be the same. So it's going to be a constant. We're going to let, what are they using as their density here? They're letting rho be the density. We figured out areas of regions in the beginning of chapter 6. The integral from a to b of top graph minus bottom graph dx. If I compute the center of mass for each rectangular strip, then I can average them by dividing them by the mass of the entire region and get the center of mass of the region. So now let's look at a single strip. Subdivide the region into individual strips. So I'm going to way that over here. Make a rectangular strip out of that so that I can compute its area real quick. Top graph minus bottom graph dx. The moment with respect to y-axis of any point in here, any value in here, let's just put a point right here for now, is a product of the distance it is from the x-axis and then the mass of that strip. That little blue line there that I've drawn or tried to draw represents how we're going to find the moment with respect to the y-axis. That distance times the area of the strip. So looking at that kth strip right there, the moment with respect to the y-axis, well, how do I compute this distance? How did we do it when we talked about radius of rotation. What did we use to represent this? The distance between the y-axis at any point in that region. This way, that's an x, right? That's an x. So we're going to take the x times the area of the strip. All right, so that's for that particular strip. So that's going to be x times the top graph minus the bottom graph. Then we're going to do this for all of the strips that we can make from x is equal to a to x is equal to b. That's the moment with respect to the y-axis. Now, the moment with respect to the x-axis, we're going to average the y's within a strip and get the average distance from the x-axis of any point in that region. How do you average some stuff? How do you average two test grades? Add together, divide by 2. I'm going to average the y values in here by adding them together and dividing by 2. So it's the average distance from the x-axis times that area. Average y in a strip times the area of the strip. So I'm going to average my y's by taking f plus g and dividing by 2. Then the area, top graph minus bottom graph ds. And then we add these up with a Riemann sum, they become an integral. And that product right there will give us the moment with respect to the x-axis for the entire region. Well, what happens if you take something that looks like a plus b and multiply with something of the form a minus b? A plus b times a minus b simplifies to
A squared plus
a squared
minus
minus b squared. So another way to look at this formula is that this is the integral from a to b of f squared minus g squared. And then I can take the 1/2 out here. All of our moments depend on the density. So I need to put the density factor in here. So let's put the density factor right here. It's a constant, we can factor it out. In some cases, in your engineering problems, it won't be a constant. It might have something to do with the order of pair. But in our problems, this is a constant right here. Then to get the center of mass, we just form the average like this. The x bar is going to be the average distance from the y-axis divided by the mass. And that's a lowercase m. And then the y bar is the average of all these distances from the y, sorry, x, divided by m. And m is density times the area. Density is a constant, I pull it out, but in your engineering practices, it's not a constant, put it back inside the middle. Take all of these centers of mass of the individual strips. This one looks like it's up here. That one looks like my this. And all those. With those intervals right there. Okay. All right, so let's take something relatively easy. Let's take an upside down parabola. Y is equal to 4 minus x squared. From x is -2 to 2. There he is right there. Nice and symmetric, even though my picture doesn't show it. assume that R has constant density of rho. So I've got a thin metal sheet shaped like that, and I want you to balance that on your finger. Where do you think your finger would have to be? Looks like it's gonna have to be on the y-axis, somewhere closer to the bottom, right? If I were to pick that up and balance it, there's more area down here than there is up there. So I'm gonna guess that my center of mass might be about right there, which means my x-coordinate, x bar, should be 0. And y bar should be a number maybe close to 1-ish, right? Well, let's go ahead and calculate it. First, let's find the mass of this region. The mass is just the density times the area. So I'm going to find the density times the integral from -2 to 2 of 4 minus x squared. Get our density times 4x minus x cubed over 2 from -2 to 2.
Is 8 over 3 minus.
So I have 8 minus 2 cubed is also 8. 8 minus 8/3 minus -8 plus 8/3. So whatever 8 minus 8/3 is done twice. 3 times 8 is 24. 24 minus 8 is 16. Done twice. I think I should get 32/3 of area. Multiply that by that constant rho. The mass of the region. That's gonna be the denominator of their calculations of finding the center of mass. Now, because it's symmetric to the y-axis, we said that the x bar was going to be 0, which means that the moment with respect to the y-axis should be 0. So let's compute the moment with respect to the y-axis. Distance from the y-axis times top graph minus bottom graph. Top graph is 4 minus x squared, the bottom graph is 0. So we're integrating from -2 to 2, x times 4 minus x squared. Right? G and all these examples, this example is 0. Put the x through the parentheses. And I have 4x minus x cubed. And when I integrate that, I get x squared times 2 minus x to the 4th over 4 from -2 to 2. Both of those powers are even. So I'm going to get the same thing at -2 that I get at +2. Is that obvious enough? So whatever number I get when I put a 2 in here, I get the same number when I put a -2, which makes that value 0. And that's what we had suspected by the picture. I should have the center of mass on the y-axis. Now, expecting my moment with respect to the y-axis to put my y-bar term somewhere in the neighborhood of 1 maybe. So let's compute that. Mx has that average in it. So it's the 1/2 comes from the averaging, the density, and then the top graph squared minus the bottom graph squared. My bottom graph is 0. So I'm gonna take 4 minus x squared and square it. Then integrate it. When you square, you get 16 minus 8x squared minus x to the 4th. I'm sorry, plus x to the 4th. I may have said minus. And then we integrate term by term. We get 16x minus 8x cubed over 3 plus x to the 5th over 5. This one has a bunch of odd powers, so I'm going to keep going. 16 times 2 is 32. 2 cubed is 8. 3 times 8 is 64. 2 to the 5th is 32. Then I should do that same thing, but minus when I put the negative 2 in there. Just calculate that stuff in the first parentheses and then double it. There's the tricky part. Let's see.
Well, if you're doubling it, then you have it anywho, can't you just ignore it?
Yeah.
Then just go with like the first bit.
Yeah. So let's do that. Help me out here. Common denominator, I guess, would be 15. That sucks.
It's 15 times 32, that's what I need to do.
I'm not doing that by hand.
Oh, God. 5 times 2 is 10.
I feel like that.
How about 480? Is that close?
Yep.
And I need 64 times 5,
320.
320. And then 32 times 3 is 96. And so 480 minus 320 is 160, maybe, plus 96. What is that? 160 plus 96, there's a 6, 256 over 15. And then I double it, because that's there, and that's a half of it. So I stick that on it, and that's the moment with respect to the y-axis. And so y bar, the second coordinate of the coordinate pair is, oops, that's x, that's mx. It's mx divided by m. So I take my 256 over 15 and divide it by my mass was 32/3. So I did the old flip and multiply. The density constants cancel. Those 8 times maybe? It comes 8 is 16 through 20. Yeah, those 8 times. 8/5. So that wasn't the neighborhood I wanted. 3/5. So I got my center of mass here. The x is 0 and y is 8/5. Okay. So the right formula is over here again. And I'll do another example. The mass is the density times the area. x-axis times the distance from the y-axis times the area. And the moment with respect to the x-axis is the density times the average distance from the x-axis times the area. Make it easier to remember. Like that, I don't know. And then the center of mass. Put in the cloud. Erase anything. Oh my goodness. Cloud. David. Let's do another example, shall we? I have my list of examples from that little handout that I gave y'all. You have them. Well, I think I have them too. Set these up. Last section 6.5 worksheet that I gave you. I got a couple of them on there. So let's look at number 1. Again, I'm bounding by the x-axis, so that might be kind of boring. So how about we do number 2? Let's do number 2. Number 2, look at the first quadrant portion between the graph of y is equal to 3x squared and y is equal to 1. So 3x squared is kind of a skinnier looking parabola. And then y is equal to 1, we'll put right here. We're going to need you to find that point of intersection.
The square root of 1/3.
Yeah, so let's fix that. Let's make this y is equal to 12. I don't want any square roots of 1/3 in my calculations. Today's Friday. You don't have square roots of 1/3 on Friday. Make that the line y is equal to 12.
Just be 2 then.
Then y is 2. I would never have my finger there because it's top heavy, right? The top is going to flop over. I need to get kind of more else here. So it should be slightly bigger than 1, maybe. Maybe around the neighborhood of 8. That's my guess. It's a fun game to play. Guess the center of mass. Who's ever the closest wins this beautiful homogeneous lamina.
Always want my homogeneous lamina.
Okay, let's take our density to be 1, so because I always forget to write it.
Case I dare you to calculate my center of mass.
All right, so because I always forget this, doesn't mean it cancels anyway. All right, you get a density from the mass, a density from the moments, and it cancels if it's constant. So let's just take it to be 1. All right, so the mass of this region is simply going to be the area. So our ratio, let's calculate the area of this top graph minus bottom graph dx. Done. Put it in the box so we don't lose it.
Should be like 16 times like the fun looking P.
but it's one, P is one. A funny looking P is called a row,
Okay, it's one.
P is one in this. All right, now, the moment with respect to the y-axis is the one that I compute next. And so we use that distance x times the area of the strip. Since it's the area of the strip, we have to do all of that inside the interval. Density is 1. Top graph is 12, bottom graph is the parabola. We'll send that x to the parentheses, then we can integrate term by term. Integrate 12x and get 6x squared. Integrate 3x cubed and get 3/4 x to the 4th to be evaluated from 0 to 2. Yes, sir.
3x cubed instead of x cubed.
I'm sending the x through there to get x cubed, and now I'm going to integrate it. So that gives me a 4 and a 4. I'm putting the 2 in there. 2 squared is 4. 4 times 6 is 24. 2 to the 4th is 16 divided by 4 is 4. 3 times 4 is 12. So that's what we get for the moment with respect to the y-axis. That was an awesome change, making a 12 out of that. Look at these nice whole numbers we're getting. Now the next one uses that average, so that one's going to have the 1/2 of the f minus g, then times the area, which is f plus g, and that generates the f squared minus g squared in here. Density as well. So our density was 1. F in our example was the 12. G was the 3x squared. So that's what we've got to integrate right there. Twelve squared is 144. 144x will be the integral of that. 3x squared is 9x to the 4th. When we integrate that, we get 9x to the 5th over 5 from 0 to 2. And here's the yucky part. 2 times 144 is 288. And this is 9 times 32 over 5. Eek. 2 times 9 is 18, 27, 28. Ah, that's not bad. So if I get a common denominator, then I've got 4 times 288 over 5. Half of 4 gives me 2. 2 times 288. 576 over 5. And then for the big finale, we divide each of those by the mass, put them in the right order, and we'll have center of this. X bar is the moment with respect to the y-axis of the mass. So that's 12 over 16, which is 3/4. Y bar is the moment with respect to the x-axis over the mass. That's my 576 over 5 divided by 16. Isn't 16 over 576? there ain't nothing hard about computing these things. It's a matter of knowing what the formulas are, and if you think of them in terms of geometry, they're easy to remember. This be something that you would consider okay to put on this first exam?
Yeah, I think so.
I mean, I don't.
Why not? Like, honestly, it's pretty simple. And
I'm just gonna have you set up the intervals, not do.
Word out.
Set them up.
Yeah, that's fine.
Is that fine? Can we go ahead and leave that? 'Cause it's
We're
only
just setting
review
them up.
sheet.
All right.
Just set up the intervals that you're gonna set up.
Wait, so are we setting up the integral for the whole test, or you actually want us to compute?
So some of the sections, computing the integral was the idea, right? Remember when we did the problems in 6.3? We had to learn how to integrate sine squares and cosine squares. So for those problems in 6.3, finding polar areas, I'm going to ask you to compute. In the arc-length section, manipulating the integrand to get it to something you know how to do, that was one of the big issues of that section. So 6.4 problems, I'm going to ask you to go all the way through. Everything else, just set them up. Set up the area integral, set up the volume by disk, volume by washer, volume by slicing integral. Set up the center of mass integrals, moment integrals, and set up, that's all. Now the two compute. Compute the area of the polar region, compute the arc length either in rectangular or and I put the big old bold letters, set up, do not evaluate.
when you say setup, you just mean quite literally like put it into the integral.
Yeah, this would be set up,
All right.
right? That's set up.
That's not too hard, Mom.
So that I know, you know, we can stop anybody from Cal One and they can do that. That's not impressive.
So the trickiest part about this all for me is the arithmetic that comes after that.
Yeah, numbers, you don't want numbers, especially on a test. Ugh.
Numbers, what are they good for? Those Romans.
That makes me feel a lot better about this test actually.
So, let's go through and talk about our test, and if you think that it's fair game to put this on there. If you have any objections from anybody about putting center of mass problems on there. I mean, mass problem on your test. Set up the integral to find the mass, one with respect to the x-axis, one with respect to the y-axis, and how do you find the x, y, y? Got it? Okay. So, you have not looked at the review sheet. That'll do me no good.
Do that right now.
I mean, I haven't had time to, I was gonna look at it tomorrow.
Yeah, we had a chemistry test. this week.
Tonight? Next week?
We had to recover.
Yeah, I had to recover.
Thursday was chemistry?
No, Wednesday.
Wednesday was the chem test, Thursday was like recovery day. Like, I'm really
You
glad.
guys are still too young for Jimmy's, right? So you recover in other ways. You like sleep or something.
I sleep.
I yell at Tristan.
Yeah, he yells at me.
Okay. Let's talk about your test then. The first thing that we covered was area. So I typically give you some equations and ask you to set up the integrals that'll find the area, first as a dx integral and then as a dy integral. And you might need more than one for either of the cases. Right? So let's do that. Let's review. So find the area of the region R, which is bounded by the graphs. X is equal to 4 minus y squared. And maybe 2 minus y squared, how about that? And x is equal to y. And in part 1 as dx, and in part 2 as dy. region R. The region bounded by x is 2 minus y squared and x is equal to y. We'll look at as a dx area and dy area. Just set them up. Set up only. The key is a nice, pretty picture with the points of intersection labeled. Does anybody know what the graph of x is equal to 2 minus y squared looks like? Which way does your parabola open up?
Left.
It opens up back toward the y-axis, right? And where is its vertex?
Two, zero.
There you go. That is x is equal to 4 minus y squared. What about the other graph? X is equal to y. Right through the origin, right? So it intersects here, intersects there, and this is the region that you want to find the area of. Right in here. So your next task, find those coordinates of the 2 points of intersection.
At top of intersection should be 1, 1.
Will you just get about eyeballing it?
Yeah.
Let's see, if x is 1 or if y is 1, x is 3, I'm not
I thought it
going.
was 2
Is it
minus
2
y
minus
squared.
y squared?
Oh, my bad, my bad. Landing over there. It's a much better number than 4, huh? Okay, so if y is 1, x is 1, if y is 1, x is 1. So I agree with the 1, 1 here. I don't agree with 1, 1 back there.
-2.
Okay, we're gonna set 2 minus y squared equal to y. Put a 0 on one side. We get that. That does factors of 2, opposite in sign that add to 1 are 2 and 1. I'll need a +2 and a y minus 1. So y is -2, y is equal to 1, we already found. Y is -2, and that's the line where x is y, so they're both at -2. So I'd have to fix that for the old test, wouldn't I?
Why?
No, because then I could tell if you were looking at the right coordinate. Which one's the easier one to do? If you were having to do the area all the way out, computing the integral, would you rather do this as a dx or a dy integral?
Probably
This is
dy.
dy simple. Imagine that thing partitioned with rectangles that are in the dy mode. Come here, baggy, open up. Let's do the dy integral first. If you do dy, the right graph is the parabola, the left graph is the line. Correct? All the way through. So for the second part, as dy, we're going to do the right graph minus the left graph. Parabola's on the right, line is on the left. Everything has to be in terms of the variable y in here. So it's 2 minus y squared. Right graph minus left graph. And then dy. What are the numbers that go on the integral sign?
Should be -2 to 1.
That -2 to that 1. And that's where you stop, right? That's setting it up. So what's the issue with the dx? It's going to take 2 different integrals because once we pass x is equal to 1, here I have line on top, parabola on the bottom. Here I have parabola on top, parabola on the bottom. And we need our equations written as functions of x. So we're going to have to take that parabola and write y is a function of x to give me the top? Y is a function of x to give me the bottom. What does the equation of the top half of this parabola look like?
I think it's negative. That would be square root of negative x plus 2.
Are you doing the solving for y in your head?
Yeah.
Let's swap places with those. Like that.
Yeah.
And now y squared is equal to 2 minus x has two roots. Positive root gives us the top part of the parabola. The negative root gives us the bottom part of the parabola. So the top part of the parabola is y is equal to the positive square root of 2 minus x. The bottom part of the parabola is y is equal to negative square root of 2 minus x. All right, so we're going to need two integrals. As you read from left to right, what's the leftmost x to that corner point?
-2.
2,
1,
and then I pick up from 1 to
2.
positive 2. Okay, on the interval from -2 to 1, the line is on the top, and then the lower portion of the parabola is the bottom.
So then there's bx plus the square root.
So x minus that negative 2 minus x. Or you can write that as x plus the square root of 2 minus x. All right, how do we do that region from x is 1 to x is 2? All right, I'm gonna have this square root sign minus the negative of it. So you're just gonna get two of them. So that's all I left room for. But I'll put the explanation as the square root of 2 minus x minus the negative square root 2 minus x. And then we can stop right there. All good? That's your 6.1 version problem.
That wasn't too hard.
All right, 6.2, let's just make something kind of easy. What's your, give me a graph. Yeah, I will need a region in the XY plane bounded by two graphs. Get the graph in your hand? Square. X squared.
Y equals x squared, so that's pretty handy.
Okay, so I need a region bounded by. Then I gotta close it up with something. Y equals 2. Y is equal to 2. Today's Friday, we do want square roots.
Or.
So how about y is equal to 4?
That's
So here's region R. Okay, region R in this first example is going to be the base of a solid. That has the property that every cross section made perpendicular to the x-axis is in part 1 a square, part 2 an equilateral triangle, part 3 semicircle with the diameter on the base.
So part square.
So a solid has its base in the shape of R. Every cross section of the solid perpendicular to the x-axis is in part A, I forgot what I said, a square. In part B, an equilateral triangle. In part C, a semicircle with diameter on the base. And I want you to set up integrals to find the volume. solid looks like. So you draw your favorite parabola, top it off by the line y is equal to 4. So if my son went bridges and sat down on the ground and got up, that's the infinite waves. Now we're going to make a slice of that perpendicular to the x-axis. Here's a typical slice. Say that has length S. And in part A, you pull that out and show it to everybody. It looks like that. In part B, pull it out and show it to everybody. There's S all the way around. And in part C, when you show it to everybody, S forms the diameter of the semis. You finished it, I'm tired. What's the idea in finding the volume of a solid with a known cross section? Base times height. So our plan is, we're gonna find the area of those shapes as functions of x, and then the height is my thickness of my slice. That's the plan. If we have a square, the integral is s squared. What's the area of an equilateral triangle in terms of its side?
One half base type s squared.
Square 3/4.
So you gave me that 1/2, and now I gotta get my fingers all dirty.
S. Put out of it. All right.
I'm gonna write it down to remember it. And now it's a semicircle.
Pi s squared. S divided by 2.
We're gonna divide the s over 2, because the s is the diameter. But it's a half because it's a semicircle. S is the diameter, so you gotta get a radius out of it. I want that black. Semicircles, pay attention that that length S is a diameter, cut it in half to get a radius out of it. In all of these examples, what is S as a function of X? 4 minus X squared, top graph minus bottom graph. What do you think the bounds on the X are going to be for the integral sign? Those two graphs intersect when X is -2 and 2. All right. So now it's just a matter of putting that in there. Okay, this part is the thinking part. You remember the formula? And now everything else is the same as it was back in 6-1, top graph minus bottom. So in this example, we're going to have the integral from -2 to 2 of 4 minus x squared dx. That's the s squared. Next one, we're going to have the integral from -2 to 2 square root of 3 over 4 times 4 minus x squared dx. minus x squared. Down here, I'm gonna have the integral from -2 to 2, 1/2 pi 4 minus x squared over 2 squared dx.
Equal to volume, right?
Those are all volume, I don't know where I have to do this. Thank you. Okay, so now let's cut our parabola in half and just take that portion of that particular region bounded by those two graphs in the first quadrant only. And let's start revolving that all over the place and make volumes of solids of revolution. So let's now consider only x positive. So we're looking over here, and that now is R. Examples. Volume. Sine. If R is revolved about x-axis, y-axis, line x is equal to 2. Line y is equal to -2. So the integral defines the volume of the solid array region. We revolve about these axes as discs or washers, and then as shells. Every way you know how. Washer. We're gonna whip these out pretty quick. Something's gonna be a disc or a washer means big radius squared minus little radius squared times pi on the outside. So we're looking here. We're looking at about the x-axis. To make a disc or a washer, do I need x or a dy partition? Right, because what's our little rhyme? Shells are parallel, disc washers don't rhyme.
I see.
So for a disc or a washer, we gotta do that. Shells are gonna go parallel. So disc washer is that means dx, correct? Why do I know that that's dx? Because that's upward, right? Dx. So in this example, it'll be dx. All right, so you tell me what the big radius is.
4 squared.
Okay, from the axis of revolution to the farthest point. And that's the line y is equal to 4. Right? So y is equal to 4. The inside radius is here, and that's the parabola. Y is equal to x squared. What numbers belong on the integral sign?
0 to 2.
There are the x's on that region, 0 to 2. Okay, for shell. Remember, we have to go parallel. Axis of revolution. And our plan for shell is 2 pi radius height, then times the thickness, where the thickness represents the dx or dy. And in this, we're going about the x-axis. And so if we're going about the x-axis here, I gotta go parallel to the x-axis. That makes everything dy. Right? And so 2 pi r always is measured from the axis of revolution, this time to the middle of the box. So depending on where I put my box, that length is r. What do we use in this example? That's going to be one of the y values there. Height is how tall that box is. So it's right graph minus left graph. What's the right graph as a function of y?
Or why?
Left graph is x is 0, and the thickness is a dy. Then the numbers on the integral sign belong to the variable y. All right, while I'm erasing, do the same thing now, but go about the y-axis. Shells and washers about the y-axis. Shells are parallel. Washers are not. This example, then, to get a washer out of this is actually going to be a disc, isn't it? I'm gonna have to go dy again. Right, the inner radius is gonna be the same as the axis of revolution, so instead of give a washer, it gives us a disc. Pi r squared thickness. And my thickness is dy. The r is going to be the length of that box. How long is that box? Spam calling me again. Wasn't here for this. Where do I? I still goes from 0 to 4. Yes, no, maybe? You guys just write that down, hoping you understand it later, or do you actually understand it right now?
I already had that written down, so
Good.
Excel.
I can make an A on this test.
I would hope so.
Hey, I didn't know.
Prove it.
I didn't say 100, I said an A.
Aren't you the one making the test?
Okay. Is there some sort of moral problem with that?
I mean, I just feel like you should be able to answer your own questions.
Ha, I laugh at that one.
She's made mistakes on her own questions before in front of us. So-
We'll talk about that, that didn't happen. You wanna get a good grade comment on that.
All right, now we're swinging that blue rectangle around the y-axis to generate the shell, 2 pi RH thickness. 2 pi RH thickness. everything you're putting in here has got to be X-ish. What's my R? Where is X? What's my H? Forgotten my equations. And then the X's go from. Zero to 2. Good. And if we move away from the axes, if we move further away, the R becomes axis of revolution minus. If we add, go below it, then if we go to the right, we subtract. If we go to the left, we add. Above, we subtract. Below, we add.
H is the 4 minus X squared.
Correct. Tells me how tall that little blue box is, top graph minus bottom graph. Okay. So on number 3, if we're going to take that same region about the line X is 2, and I want a washer. We're gonna go perpendicular, shown, we're gonna go parallel. So for the washer, they have to go dy, right? That little blue line's perpendicular to the dotted line. So the washer is pi outer radius squared minus inner radius squared, and in this case, dy. So the outer radius has to go from the axis of revolution to the leftmost part of the blue box. So how long is that big R?
2.
2. 2 units away. So big R is 2. What about little r?
X minus n squared.
2 minus, not the square root of x. 2 minus, everything's dy here,
X squared root of y.
square root of y. Right, there's a little r right in there. So I, worker, you're not worth a hoot. 2 squared minus 2 minus square root of y squared dy from what to what?
0 to 4.
Agree. 4. Shells are parallel, so we take that region and we dx it. So there. So the H stays the same. R now is right graph minus, or right axis of revolution minus the X. So R is with my axis of revolution 2 minus X. Height is top graph minus bottom graph. What's the top graph again? Y is 4. And so volume is 2 pi RH thickness. So it's 2 pi 2 minus X, 4 minus X squared. And the numbers on X were, there's 2. Okay, so if your region is here, and your axis of revolution is me, that's axis of revolution minus X. If your region is there, and I'm your axis of revolution away from the y-axis, your Radius is X plus my distance. Okay? Same thing here, with this one. If I'm revolving this up here, my radius is Y value minus whatever that Y value is, Y. So line minus Y, my axis is here, it's Y plus whatever equation is there. Okay? So I'm not gonna do the other part. Because I want to keep talking about the rest of the test. 6.3, I want you to be able to change something from polar coordinates to rectangular coordinates, like our ordered pairs, and vice versa. I want you to be able to sketch the basic rows, the rows curves, cardioids, circles, or the little figure eight one, the R squared is equal to something.
Laminar or something.
Yeah.
Let me see.
Then I want you to be able to find the area bounded by one of those figures. 6.4, make sure you know the two arithmetic formulas, one for rectangular coordinates, for polar coordinates, to be able to integrate those on the way out. 6.5, work done with a variable force, work done with a constant force like it's pulling up a chain, work on a spring, work in pumping liquid, fluid force, center of mass. Okay, minor dilemma possible.
I heard.
I'm going out of town for the weekend. We got a well-lit party coming up. And I'm supposed to be back on Monday. But you saw that movie with the guys went to Las Vegas for this bachelor party. If I don't make it back, well, I don't have anybody to come to your house. So the problem is, I want you to check your email Sunday night and or Monday morning. If I can't make it back in time, I might have to deliver your exam online, which means I would post it on Blackboard and you would log into Zoom and take it in your room.
Okay.
I'm fully anticipating that. It's not up to me. If I get a roofie, what do I do with it? No, but we're not getting you, but please check your email Sunday night, Monday morning to make sure that we're all gonna be here.
Well, I'll be hoping you don't get food.
I'm not. Oh, very intense.
Oh, I've got papers, those of you that turn them back and I can't see.
Right up. That's something I need to do.
The list of papers that I
And Lindsay, and Kaden. Stack for me. I can't see again, at least yours is big. Right there, I got staple.
I can extract this.
All right, thank you.